State and prove the Laurent's theorem. If f of z is analytical inside and on the boundary of a ring-shaped ring are bounded by the two concentric circles C1 and C2 with the center at A, and R1 and R2 be their respective radius, R1 and R2 the respective radii with R1 greater than R2, then for all z in R, f of z sigma n varies from 0 to infinity a n bracket starts z minus a bracket close raised to power n plus sigma n varies from 1 to infinity a minus n upon bracket starts z minus a bracket close raised to power n, where a n is equal to 1 upon 2 pi iota integral over c1 fw over bracket starts w minus a raised to power n plus 1 dw, n is equal to 0 1 2 so on, and a minus n is equal to 1 upon 2 pi iota integral over c2 fw over bracket starts w minus a bracket close raised to power minus n plus 1 dw, where n is equal to 1 2 3 so on. Now proof C1 and C2 circles radii R1 R2 A the center Z contains in R. By the Cauchy's integral formula we have f of z is equal to 1 upon 2 pi iota integral over C1 fw over w minus z dw minus 1 upon 2 pi iota integral over C2 fw w minus z dw. These are the two parts we will solve one by one. Now considering the first integral, in we have this 1 upon 2 pi iota integral over, in this 1 upon w minus z is equal to 1 upon w minus a minus z minus a is equal to 1 upon w minus a taken common, so it is equal to 1 minus z upon v z minus a upon w minus a square bracket. Now taking this into numerator, so it will become equal to 1 minus z minus a upon w minus a whole raised to power minus 1. Now solving this is equal to 1 minus w minus a square bracket 1 plus z minus a upon w minus a plus z minus a upon w minus a square plus so on, plus z minus a upon w minus a raised to power n minus 1 plus z minus a and w minus a raised to power n into 1 upon 1 minus z minus a upon w minus a square bracket close is equal to 1 upon w minus a. Here in this last term we have calculation of w minus a minus z plus a upon w minus a, and rest of the terms are same as it, so it is equal to 1 upon w minus a 1 plus z minus a w minus a. So this term will come into numerator, and this is in we remain with the w minus z. Rest of the terms are the same as it is, so it is equal to now multiplying with 1 minus wa, so it is equal to z minus a upon w minus a square plus z minus a square upon w minus a cube plus so on, w z minus a raised to n minus 1 upon w minus a raised to power n plus the z minus a raised to power n upon w minus a raised to power n, or w minus z. This is equation 2. So 1 upon 2 pi iota integral over c1 fw w minus z dw is equal to first integral part of this one is equal to 1 upon 2 pi iota integral over c1 fw over w minus a dw plus z minus a over 2 pi iota integral over c1 fw over w minus a whole square dw plus so on z minus a upon 2 pi eta raised to power n minus z minus a raised to n minus 1 upon 2 pi eta integral over c1 fw over w minus a raised to power n dw plus un which is equal to a0 plus a1 into z minus a plus so on plus a n minus 1 bracket starts z minus a bracket close raised to n minus 1 plus un is equation 3 where a0 is equal to 1 upon 2 pi iota integral over c1 fw over w minus a dw. A1 is equal to 1 upon 2 pi iota integral over c1 fw over w minus a square dw, and similarly a2 is equal to 1 upon 2 pi iota integral over c1 fw over w minus a cube dw, so on an minus 1 upon 2 pi iota integral over c1 fw over w minus a raised to power n dw, and un is equal to 1 upon 2 pi iota integral over c1 z minus a over w minus a whole raised to power n fw w minus z dw. Let us consider the second integral in the one in this second integral we will consider now. For this interchanging w by z in equation 2, in this equation 2 we will replace w by z and z by w, z by w and w by z, z by w and w by z. So we have for this interchanging w and z in equation 2 we have 1 upon w minus z is equal to 1 upon z minus a square bracket 1 minus w minus a upon z minus a bracket close square bracket close is equal to 1 upon z minus a plus w minus a over z minus a square plus w minus a square over z minus a cube plus so on w minus a raised to power n minus 1 upon z minus a raised to power n plus w minus a over z minus a raised to power n into z 1 upon z minus w, so that 1 upon 2 pi iota integral over c2 fw w minus z dw is equal to 1 upon 2 pi iota integral over c2 fw over z minus a dw plus 1 upon 2 pi iota integral over c2 w minus a over z minus a whole square fw dw plus so on plus 1 upon 2 pi integral over c2 w minus a raised to power n minus 1 over z minus a raised to power n fw dw plus vn is equal to a minus 1 upon z minus a plus a minus 2 upon z minus a square plus so on a minus n over z minus a raised to power n plus vn is equation 4, where a minus 1 is equal to 1 upon 2 pi into iota integral over c2 fw dw, a minus 2 is equal to 1 upon 2 pi iota c integral over c2 w minus a fw dw, and so on. A minus n is equal to 1 upon 2 pi iota integral over c2 w minus a raised to power n minus 1 fw dw, and vn is equal to 1 upon 2 pi iota integral over c2 bracket starts w minus a over z minus a whole raised to power n fw over z minus a dw. From 1, 3 and 4 we have f of z is equal to square bracket starts a0 plus a1 into bracket starts z minus a bracket close plus so on plus a n minus 1 bracket starts z minus 1 bracket close raised to power n minus 1 square bracket close plus square bracket starts a minus 1 over z minus a plus a minus 2 over z minus a square plus so on plus a minus n over z minus a raised to power n square bracket close plus un plus vn is equation 5. Now the required result follows if we prove that limit n tends to infinity un is equal to 0 and limit n tends to infinity vn is equal to 0. To prove limit n tend to infinity un 0, since w is on c1, so modulus of z minus a over w minus a is equal to gamma is less than 1, where gamma is a constant. Also we have modulus of f of w is less than m1, where m is a constant, and w modulus of w minus z is equal to modulus of w minus a minus z minus a, which is greater than equal to r1 minus z minus a modulus, where r1 is the radius of c1. Hence we have modulus of un is equal to modulus of 1 upon 2 pi iota and modulus of integral c1 bracket starts z minus a over w minus a whole raised to power n fw over w minus z dw modulus close is less than equal to 1 upon 2 pi modulus of integral over c1 modulus bracket star z minus a over w minus a whole raised to power n fw over w minus z dw modulus close is equal to 1 upon 2 pi gamma raised to power n fw case of m and w minus z is r1 minus z modulus of z minus a, and integral over c1 fw dw is equal to 2 into 2 pi r1, which is equal to gamma rn m r1 upon r1 minus modulus of z minus a. So limit un tends to 0 to limit n tends to infinity un tends to 0. So proving the limit n tends to infinity vn is 0. Since w is on c2, so modulus of wa minus z minus a is equal to n, where n is less than 1, where n is a constant. Also we have modulus of fw is less than m, so here m is a constant, and modulus of z minus w is equal to modulus of z minus a minus w minus a, modulus which is greater than modulus of z minus a minus r2, where r2 is the radius of c2. Hence we have modulus of vn is equal to 1 upon 2 pi modulus of integral over c2 w minus a over z minus a raised to power n fw over z minus a dw modulus close is less than equal to 1 upon 2 pi neta raised to power n m z minus a minus r2 2 into 2 pi r2, which is equal to neta raised to power n m r2 modulus of z minus a minus r2. Then limit n tends to infinity vn tends to 0. Therefore from 5 we get f of z is equal to sigma n varies from 0 to infinity a n bracket starts z minus a raised to power n plus n varies from 1, sigma n varies from 1 to infinity a n minus n over z minus a raised to power n.